This is Free Range Digital Design Foundation Modeling, Chapter 23. We have arrived at finite state machines. This is where we'll spend the rest of the text. So let's do it. So we've been working with circuits, and we've kind of seen that circuits, digital circuits, are a bunch of modules controlled by something. So up till now we've had three forms of control. We consider node control one of those forms. Also external control and internal control. And so any circuit can have combinations of these, either node control or a combination of external and internal control. FSMs in general, they provide circuit control, and so we'll see that in later chapters where we use FSMs to control circuits. So FSMs can be used for a lot of different things. We are going to use it initially as an approach to design counters, and then we'll get into controller designs. This is a picture from chapter 1 in this book, which we have a bunch of modules here that's being controlled by something. So these modules could be sequential circuits, combinatorial circuits, or I've listed computer peripherals there also. Could be some external circuit that's pre-made or pre-modeled that you're using. But they're all controlled by either a finite state machine or a microcontroller. So this course is about controlling circuits with a finite state machine. Certainly that's a hardware approach to controlling things. If you control a circuit with a microcontroller, that's more of a software or firmware approach to controlling things. Circuit is just follows our model we've been working with. We've got data coming in, data coming out, control coming in, and status coming out. So by all means, you have a controlled circuit that could be some part of some other bigger controlled circuit. Now FSMs, the approach we'll take is very simple. Structurally, they're just three modules. There are two decoders and a register. So the registers, of course, are sequential circuits. Decoders are combinatorial circuits. So what we'll start with is kind of a medium level approach on this. Now this is different from most of the other books where they have you design these state machines using flip-flops and external logic. We'll kind of bump it up a level. We'll primarily be using registers and decoders. I hope to develop a intuitive feel for these. What we'll be doing is a bunch of examples. This is actually a very important chapter because it shows the foundation of state machines, and not necessarily the approach we'll take later, but it gives you a foundation of how state machines operate on a low level, and that's going to help you use them to control the circuits. So once again, two steps in working with state machines: understanding the underlying design and then being able to use them to control circuits. This is our first example, and what we have here is a counter design. So a counter is a device that implements a sequence of outputs, which we'll call the count. And this happens to be an up counter. It's counting 0, 1, 2, 3, 0, 1, 2, 3. That's all it's doing. What we have here is the count changes synchronized with the clock edge. So, and what we have in this one, I think it calls out a rising clock edge. So it calls out a rising clock edge. So when the clock edge has that rising edge on it, that means the counter is going to increment. And here's an example of that. This is kind of the next slide of the solution of this one. You can see that the count is going 0, 1, 2, 3, 0, 1, 2, 3, etc., etc. But all those changes in the count are synchronized with the clock edge, as the causality arrows are showing there. You know, always the first step in these designs is to draw a black box diagram. There it is. We don't have to worry about it. But I think the next step is to draw a state diagram. So the issue in this counter is it's obviously a decimal count, but we want to implement that in hardware, which means we have to use binary. So 0, 1, 2, 3, 0, 1, 2, 3, that's going to be, it's going to require me 2 bits to do that, and that's going to be 0, 1, 2, and 3, and so these are my binary output values. That's the binary count I'm looking for. So what I'm going to do in this is step 1. I see 4 states there. Makes sense because there's 4 numbers in the sequence. So I'm going to go ahead and draw going downward just to save space. These are my 4 states. I'll give them names. put some output on these things. So what I've indicated there is the states, and I've listed the output directly inside those states. So it's a good way to do it. And I have to show some transitions here. Here are my transitions. It goes from 0 to 1, 1 to 2, etc., etc. And I need conditions on those transitions. So this circuit has no conditions, but I need to list that it has no conditions. So I essentially put these don't cares on it. So these represent unconditional transitions. And my diagram is done. So the next step is to realize that, as you can see from the timing diagram here, it's memorizing these count values. It keeps memorizing those and updating those every clock edge, which means essentially I have 2 flip-flops in there. There's 2 bits in there. I have 2 flip-flops. So there's my rough diagram. I have 2 1-bit storage elements. I arbitrarily named them Y0 and Y1. Put a node on there. So the issue here is this is going to store the count. For example, so when the count is, say, 0, 0, I want the next count to be 0, 1, which means I want the inputs, these D flip-flops, when the outputs are 0, 0, I want the new inputs to be 0 and 1. It's 0 and 1, I want to go to 1, 0, and this is the type of operation I want to enforce on this thing. So I'm going to put this in a table. This happens to be the present state and the next state. So when the present state is 0, 0, the next state needs to be 0, 1 because that's my count. So what I'm saying is when 0 and 0 are stored in these flip-flops, what I want to store next is 0 and 1. So that would mean that needs to be a 0 and that needs to be a 1, which I've done that. So I'm going to keep filling in this table, which is going to describe the flip-flop. 0, 1, 1, 0, 1, 0 goes to 1, 1, 1, 1 rolls over to 0, 0. This is very important. This is my PS-NS table. I will be using those quite a bit the rest of the course, and eventually we'll pop up to a higher level on these, but right now this is what we got. So this is a table. Once we have anything in a table, that necessarily makes it into easy design for decoder. So this is my, I'm going to plop this in here, and I'm going to call this the next state decoder. The outputs of this decoder are, these are the outputs and these are the inputs, which means I've got to feed these guys around to the back, and I think I am officially done. Okay, so that means outputs of these flip-flops, which is the current state, feeds back around to the inputs of this decoder. Decoder decodes it and puts the proper next state values on the inputs to the D flip-flop. We'll take an example here. We'll look at this row. Y1, so essentially Y1 is a 0 and Y0 is a 1 from this row. Okay, so that means Y1 plus is going to be a 1 and Y0 plus, which is next state, is going to be 0. So these outputs, these values are sitting on the input and they will be latched into these registers on the next clock edge. Once again, this is kicking out the state of this thing is the present state. The output of these decoders is the next state. The output of those decoders connects to the inputs of the D flip-flops. And once again, this is the final problem here. This is the counter, how it's counting. Remember, this is essentially count that's been expanded outwards. So we put the causality arrows in there. These conditions are unconditional, which means there's a clock edge causes a transition. This is our second example. This is similar to the last counter, but it has an extra input. It has this active low reset input. So the issue here is it's very much the same as the last one, except this one has some conditions associated with the transitions. And the condition is the reset input, and so it happens to be active low input. This is still a 2-bit binary up counter, which means it's counting 0, 1, 2, 3, and what else is there? It says use D flip-flops. Everything's pretty much the same. So first of all, let's design a state diagram for this. So if we do this, I know there's 4 states because there's 2 flip-flops, which means there's 2 raised to the power 2 different possibilities of those flip-flops could be, which is our 4 states here. So this is 0. There's our count. We need the transition arrows, so this is going to be a little bit different than before. So if we're in, we'll start here. If we're in state 1, and to get what gets us to state 2 is the fact that the reset is officially turned off. Okay, if I'm in state 1 and the reset is turned on, remember this is a synchronous reset. It's very important that it's synchronous. If it was asynchronous, we'd have a different issue, but it is synchronous. Okay, so there's a condition associated with these transitions now, and this is going to be similar to the other states. Once again, I'm in state 1. If someone turns that reset on, if someone asserts that reset, I'm going to go back to state 0. So I'm in state 2. What gets me to state 2 is the same condition if the reset's turned off. If that reset's turned on, I should say if that reset is asserted, I go back to the 0 state. And lastly, I'm in state 3. It doesn't really matter if the reset's turned off or not. I am always going to unconditionally transition from state 3 to state 0. So that's really important. Now, you don't always need conditions associated with these states. You can have conditions sometimes and no conditions other times, which is what we have in this circuit. Very similar to the last circuit, we have 2 flip-flops. It's a 2-bit counter. Put some information in there. And so we next need to put some logic in here, which we know from the last problem, it's going to be a decoder. And so the issue in this problem is, this is y0 plus y1 plus. Okay, so that's very similar to the last problem. The difference between this problem and the last problem is that output, or the next state, is now dependent upon 3 things. One being the current state, which is 2 variables here, and also it's the reset. The reset is going to be an input to this decoder. So we've got it set up such that we can set up a table. So here we go. Here is my table. Keep in mind that this is the present state, this is the next state. Now there's no reason to have reset in the next state. The state is a reset is only an input to this decoder here. Anytime reset is a 0, I know that's the asserted state of the reset. In fact, I could put the bar over it to remind me. That's the asserted state, and so the transitions are always going to be to 0, 0. Because once again, in this half of the truth table, the reset is asserted, which means the next state is always going to be 0, 0, which is the reset state. And here, this is going to act just like the previous counter, because these 4 conditions, by the way I made the table, the reset's always turned off. So it's going to transition. It's a normal counter in the second half of the table. It's got 0, 0, 0, 1, 1 goes to 2, 2 goes to 3, and 3 goes back to 0, very much like the last one. So there it is. We've got a table. The table defines a decoder. Here's my decoder. And for example here, when the reset is turned off, the 2 inputs are 0 and 0, which is 0 and 0. And the next state is going to be 1 and 0. And that's how this is going to work. All the transitions, once again, are synchronized with the clock edge. And let's look at the timing diagram. Here's your associated timing diagram. Once again, everything's associated with the clock edge, but we have to worry about this reset input. So anytime the reset is asserted, it's going to reset. So here we go. This is reset is turned off right here, and therefore the count is going to reset. It goes from 2 to 0. Usually it goes from 3 to 0. This is going from 2 to 0 because the reset is asserted. So the reset's not asserted. It's a normal counter. Once again, the reset gets asserted right here. It's going to cause the counter to reset once again. What else is fun here? The reset turns on, then it turns off. It missed the clock edge here. Therefore, this little blip in the reset input doesn't do anything. It's because it's synchronous. Because the reset is synchronous, it's waiting for that clock edge. It doesn't get that clock edge, so it actually has no effect.